All right. Welcome, everybody. This is section 9.10. Let's start the slideshow. Okay. So once again, this is just a continuation from a previous section where we learned Taylor and Mclaren polynomials, and it's the exact same formula. Now we just call it Taylor and Mclaren series. And this is what we plan on doing today. The only thing different from this in the polynomial section maybe is this thing at the end here. It's a basic list of Taylor series that you can use to solve or find series for problems that not necessarily may not look like a Taylor, or they're like a Taylor, they're just a little bit different. Okay, so going to our first, if it lets me. Here we go. So once again, this is very similar to the polynomial. Down here, we have function, we take the derivative of function, we put x minus whatever c is, second derivative, and whatever the second derivative, you can see right here, here's the first function. If you put a 0 in the first one, and then you put a 1 in the first one, this is over 1 factorial. This is over 0 factorial. 0 factorial equals 1. 1 factorial equals 1. Then 2 factorial, and so on and so on. Second derivative, third derivative, fourth derivative, finally the last term derivative. And we're plugging c in there. So this is the formula. We do need to have that written down and use that. And once again, it's really similar to the polynomial forms. All right, so the definition of the Taylor and Mclaren. Once again, if C equals 0, then we call it a Mclaren. So that's the main thing. Taylor is a Mclaren, or a Mclaren is a Taylor. It's just where C equals 0. And once again, C is in the formula. We're just going to plug it in. And normally they tell us what C is. So use this function and find the Mclaren series. Once again, Mclaren series is when C equals 0. And they want us to use this function. And I think they go through the whole thing. Let's see if they do. They do, good. Here's the function, here's the first derivative. If we have our function sine, the derivative is cosine. Do they have more? They should have more. Yeah, they do. And then the derivative of cosine x is negative cosine x, derivative of negative cosine x. Negative sine x is negative cosine x. And when you plug 0 in, this is what they get. And if you look, it looks like one of those alternating series, plus, minus. And they do even more. They go pretty far on this. So if we look at the next page on the slide, they take it a little further to the fifth derivative and so on. And once we do all the work, we plug 0 into the sine of x. Go back, if you want to go back to look. Why doesn't it let me just go back? There we go. So we start out with sine x, there's the first. Sine x, we put 0 in sine x because it's Mclaren, so we're going to say C equals 0. We get 0. Cosine of 0 is 1 once again, and then we go back and forth. So I just wanted you to see that. So when we move on. We have it all laid out. So if we get rid of the 0, so here's a 0, 0 times x squared cancels out, 0 times x to the 4th cancels out, 0 to x to the 6th cancels out, turns into 0, disappears. And then we're left with this part here. And once again, the cosine of 0 end up being 1. If you look at our formula, and our actual formula pulls an a sub n at the very end, right? I'm going to rewrite the formula up here. It was f of c plus f prime c, where x minus c, then f prime prime of c, where then you take 2 factorial x minus c squared, then you do the third derivative, plug c in there, is going to be third derivative, third factorial x minus c to the third, and so on. It ends up being this. The last term in that series. It ends up being this. So you look at this, this pattern that you see here. You're looking at this pattern, and they've created this summation out of this pattern. And here's the summation that we're looking at, and is from 0 to infinity. And we want to see, once again, this should be 1 factorial. This below it should be 0 factorial. And so this really isn't part of it. But when we look here, if we plug 1 or 0, let's say we start off by plugging 0 into here, that turns to 1. You plug 0 in here, you end up with, you get -1 to the 0 power is 1. You plug 0 into here, 2 times 0 is 0 plus 1 is x to the 1 power. You plug 0 in here, you're over 1 factorial. So you do get, when you plug 0 in, you do get this first term, or the second term. You can count this as the first. Next, if you plug the second derivative, if you do the second derivative, that was, what is it, sine. The second derivative ends up back with a negative sign, but the sign of 0 is 0. And that cancels that out. Then you get the third, and then you get the fifth. You see how it goes from negative to positive to negative. Positive, and then the second term later will be negative, second term later will be positive, and so on and so on. And same thing here. If you put 0 in here, you get that 1 factorial. If you look at the second term, then well, putting now 1 in here, if you notice, you get 3. See, this leads to this down here. So we put 0 in there and we got this term. We put 1 in here, you get a -1 to the 1 power is the negative. Put a 1 in here, you get x to the 3rd power. Put a 1 in here, you get 3 factorial. And then you can go on to the next one. The next one won't be the 4th, it's going to be the 5th power because this turns to 0. So once again, if you put, this was the first term, this was the second term, this was the 3rd term, or no, this was the first, the second, and this is, I'm sorry, I'm confused here. We put a 1 in here. We put n equals 1 here. We put n equals 0 here. So now we're going to put n equals 2 here. And if you put a 2 down there, you end up with 5 factorial. If you put a 2 up here, you end up with x to the 5th power. You put a 2 in here, -1 squared is a +1. So then the x to the 7th term would be n to the 3rd, if you look at that. So this is the summation of the series. And it does it really good. You want to try to create this by not using the zeros in there. So you have to create that from using this. And then it goes on to tell you, hey, by using the ratio test, remember the ratio test is by dividing. When you divide this by the next term, you verify that the ratio test, whether it's greater than 1 or less than 1, and all that. So we're just using the result. We're using the result to create the summation. And you see there's lots of terms missing. Every 0 won't be part of this. Oh, Lordy. And before we go to the homework, I did want to show this. This is the power series for elementary functions. Once again, we just did the sine x, and this is the sine x. This is the a sub n. This is what it looks like where you can do the summation of all the terms. And if you look, cosine of x is the same thing, pretty much. It's a little different. We start at cosine, and you go to sine. It'll be negative, and so on and so on. And then they have other ones that we could be using. I mean, here's arctangent, arcsine. Again, it's a little confusing. This is just a power series. E sub n is a good one. And then we have just a couple of others that you can take a look at. Natural log. But in the homework, we're going to be using this power series, or this, what do they just call this? Just the basic list of Taylor series to create to create a list of terms or another series from this. And so here's one that we can use. If you read the instructions in the homework, it'll be similar. Derive a power series from the basic list. So that we have the basic list. Now you want to derive a power series from that. So what we're going to do is first we're going to just look at the basic series cosine x. If we go back, see, this is the cosine. We want to find the power series for cosine of square root of x. But if we go back to the cosine of x, that's a given. We know what it looks like. We know what the summation should look like also. So this is what they should look like, just cosine x. So we have to change it a little to change it to the cosine of square root of x. So you can go ahead if you want and take take the derivative of all of this, and you would use a power rule, cosine of u, where u, once again, u equals x to the 1/2. So the derivative of u equals 1/2 x to the negative 1/2. And so on and so on. When you put that all out, this is the cosine x power series. And it's going to show you what we do. Instead of the x, we're putting the square root of x in there. So everywhere, do you see, you don't have to go through. Normally, to find this, you would take the derivative of this, then you would, and then you take the next derivative, then you take the next derivative and the next derivative. But you don't have to do all this. Since it's so similar to just the cosine of x, you take the cosine of x, this is it, and then you pop in the square root of x into the system. So this becomes 1 minus x squared over 2 factorial, put the square root of x in there, plus x to the 4th, put the square root of x in there. X to the 6th, square root of x, square root of x to the 8th. And when you do that, the square root of x to the square, x to the 1/2 square cancels each other out and turns into 1. So when you plug the square root in here, it turns into x to the 1 power. And that's what you get down here. Square root of x to the 4th power equals x squared. So this changes to x squared. Once again, this changes to x3, and take the square root 1/2 to the 8th power, you get to the 4th power. So this is the new series that we have. This is our new series. So you can use this basic list and don't have to go through the whole process. You can just plug into the x's that you see, whatever x they have. And in this case, they had the square root of x. Or you can go through the whole process again. And I think it's a lot easier by using that basic list to go through that whole process. And then I think we showed at some point where the cosine of x converges. And so because x is greater than or equal to 0, it says this series also converges. And so using that basic list, I think is going to be helpful. I'm going to keep that basic list around because I think we're going to use it on a couple of homework problems. There's only 4 homework problems. If I can find them now, let me get to the homework. Where is the homework? Did I? Guess I have to go back to it. I thought I had it out. All righty. Just waiting it for load. And I think there's only 4 problems here. I'll do 3 of them or so, or just look at it. So if we look at this function, it says use the definition of a Taylor series. And it's C equals 0. If f of x equals e to the 6x, then the derivative, if you use the power rule, right? If you use e to the u and u equals 6x, then du equals 6. So this becomes 6e to the 6x. 36, bring the 6 back down, 36 e to the 6x. Whatever 36 times 6 is. I think, oh, they show us down here, 216. 216 e to the 6x. And so on and so on. So if we start, let me go ahead and put the formula up. Okay, let's see if I can get it all in this. I don't know. X minus c over the next one, 3 factorial, and so on and so on. So first, if we put 0 in here, put 0 in there, 6 times 0 is 0, e to the 0 power is 1. Put 0 in here. Once again, e to the 0 power is 1. We have a 6. So this becomes 6. And then x minus 0. C is 0. Here we end up with 36. X minus 0 squared over 2 factorial. This one was 1 factorial. And so on. So you end up with 1 plus 6x plus 36x squared over 2 factorial. Plus the next one would have been 216x3 over 3 factorial. If you'll notice, this is the series down here. And we want to use this. We want to use this somehow to create the summation. So I think this might be the hardest part of the problem. We need to use this to create this. You have to create this on your own here. Now, don't forget, the formula from the Taylor series is f of n, f to the factorial, and c x minus c to the n power over n factorial. if you look here, when we put 0 in to n, and since we're doing 0 first, you get the 1. Then if you put 1, you get 6x. Then if you put a 2, you square this and you square this. So the 6 gets squared and the x gets squared over then the square factorial. The next one, the 6 gets to the third power, the x gets to the third power over 3 factorial, and so on. So you have to look at this. This is 1 power, this is 1 power. So if you notice, both the 6 and the x is 1 power, both the 6 and x is 2 power, both the 6 and x is 3 power. So that's how they ended up with the summation. The 6 and the x both are to the n power, and whatever we took that derivative, that's going to be down here, the end factorial down here. So if you look at that, this is how we ended up getting this. And I mean, I think even if you wrote it like this, which is mathematically the same, I think the homework would mark it correct if you put this in here. I think the homework would mark it correct. But the goal is to get enough problems in this sequence to where you can see what the summation would equal, where you can picture what's causing the summation to be the same just by adding a number in it. So that's the key, I think, is to getting enough of these and seeing what happens. The 6, we squared it, then we cubed it, then we fourth powered it, and we did the same thing with the x's. Looking at number 2. Once again, you're just going to have to take the derivative. The easiest way to take the derivative of 6 over x like this is bring the x to the top. So the first derivative would be negative 6x. And then you subtract 1 to the negative 2 power. The second derivative, then bring the negative 2 down and you end up with 12x to the negative 3. Next derivative, bring the negative 3 down, you end up with negative 36x to the negative 4, and so on and so on. So when you put this all together, once again in the formula, and I like to write it out. I know it might seem redundant, but I like to put it all in there for us to see. And so on and so on. There's more. I mean, I could write this on forever. And this time C equals 1. And so this time C equals 1. So in the first one, if I put a 1 in here, let me change my color. If I put a 1 in here, I end up with 6. In the second one, if I put a first of all, the C equals 1. So we put a 1 in here, we're going to get x minus 1. And then if we put the 1, because C equals 1 each time, if we put a 1 in here, you end up with the negative 6. You you end up with a 1 in here. You end up with a 12 over 2 factorial x minus 1 squared. And you can see this is leading to the pattern that we have going on here. And you really have to take these patterns down as far as you can go. If you look, this, yes, this is a pattern, but there's more you can do if we just focus on this part right here. 2 factorial is 2. 12 divided by 2 is 6. And you see the first term was 6. The second term was minus 6x, x minus 1. Then this was the third term. And here, if you 3 factorials, 3 times 2 times 1, 3 factorial 6. 36 divided by 6 ends up being 6. So we still end up with a 6, but a negative this time. X minus 1 to the third. And if you keep on going, you'll see the pattern is going to be the same. There's always going to be a 6 here. And the signs change. So since the signs change like that, and we're going from n0 to 1, you can see this is where n equals 1. This is where n equals 2, and so on. So since the signs are changing, we know we're going to have in our summation, we're going to have a negative 1 to the n power. You know, when it's even, you end up with a positive number. When it's odd, you end up with a negative number. If you look at this pattern, there's always a 6 in front. And then we have the x minus 1 for all of them. And the only thing different is, once again, this is, you have an n of 0 here. N of 0 here because x to the 0 power equals 1. And there's the n of 1, there's the n of 2. So this goes to the n power. So you could almost create this, you know, what I would do is take it all the way out. And if you look at it like this, take it all the way out, it might be a little harder. You said, oh, you're multiplying it by 3 then the next one, you'd be multiplying it by more. Take it out a couple more spaces and you'll see that they all cancel out. It all cancels out to look like this. And that's what you're doing. You're trying to make it in its simplest form so you can see the pattern. And this is the summation pattern that they would use, the A sub n. That's the summation. This is what I got, and it's what they got also. So this is what you would type in over to here. So you can't just look at this and say, oh, what's the pattern? You have to see if any, if you look at this, you want to see if anything cancels, and it does. You want to see if anything cancels, then the pattern will be more apparent to us. Then the pattern would be easier to see. I'm not going to do 3, but I do want to do the last one, 4, because the last one, 4, says use the table power series from the elementary function. So we're going to use cosine 6x. And if we go, once again, if we go back to the power series, I'm just going to bring it up for a second and look at the cosine. So if you notice, we're going to bring this into our problem. So we're going to start off by bringing that into our problem. If it lets us, there we go, yes. And here's what they did for cosine. And once again, the only thing is, instead of a square root, I think we did last time, this time we're going to put 6x in there. And here, if you put 6x in x, nothing changes. Here, if you put 6x in there, 6x squared, the 6 is squared, and the x is squared. So that's what we get. And once again, they don't show us we have those missing pieces, but we don't care about those because we're just plugging 6x into each one. We don't have to go through that whole process again. All we have to use is from the easy list, or what do they call it? The elementary functions, using the table from the elementary functions. And now I just put 6x in here. And once again, 6 to the 4th power. I'm sure it's 1296. They show it there. Yes. So we put 6x to the 4th power, and we get 1296, x to the 4th power. And don't forget, that's going to be over n to the 4th power, which is n factorial, 4 to the factorial. There. Okay, so now that we have the list, it functioning, now that we have it started, we have to create that summation that we're looking for. And usually the first one doesn't help out much. But once again, if you notice, it has an alternating sign. So we know the summation is going to have -1 to the n power. As long as you have that alternating sign, you're going to have that -1 to the n power. It could be an n plus 1, depending on the numbers and all that. It definitely looks like n power. And we're going to go from 0 to 1. If we put a 0 in here, -1 to the 0 power equals 1. That's what we got here. Next, if you look, we know there's going to be a 6x because we're taking 6x to a certain power all the time. So we're taking the 6x to a certain power. We just have to be careful. So when I plug n1 in here, we're going from n0 to infinity. If I started off with n0, and we get 1 at the first. We get n equals 1. We don't get n equals 1. We get the answer equals 1. The whole thing equals 1. Now, if I put n equals 1 in here, if you look, I start if odd numbers are negatives. So do you see this is an even number? If I say n equals 1, I put n1 here. If I put n1 here, n equals 1 right here, I end up with 6x, but I can't have a 6x. I have to have 36 at that point. So I have to square that. So when I put a 1 here, I have to have it squared somehow. And the same thing, if this is going to be n0, this is going to be n1, this is going to be n2. And even for n2, we have to square it to get 4. So one way of doing this, we know this is going to be n, but the 6x, we have to have something here other than n. And we can, and if you look 2n, now if I put an n1 in here, I square the 6 and the x, and that's what I'm looking for. If you put an n1 in here, you get the negative, you get the 2 squaring the 6 and the x, and then don't forget, it's always going to be the next factorial also. So since this is n1, this is going to be n1, this is going to be n2, we're doing the same thing down here. We're doing 2 times n. We're doing this same thing that's up here, down below with the factorial. Because now if I put a 1 in there, I get 36 x squared. Put a 1 in here, I get 2 factorial. I put a 1 in here, I get a -1. I'm just going to put a -1 like that. Now, if I put a n2 in there, I get a +1. Put a 2 into here, I get 6x. 2 times 2 is 4, so I get 6 to the 4, which is 1296. I get x to the 4. And then I put a 2 down here, so I get 4 factorial. And so that looks like the answer. So this looks like the answer, -1n 6x to the 2n over 2n factorial. So, I mean, it takes a little thinking. It takes a little thinking of, okay, you have to have n, in this pattern, you have to, since we're doing summations, you have to start with 0. This has to be n1, this has to be n2, and so on and so on. And you have to create this summation for that. You have to look at the pattern to create the summation. I mean, the negative part was easy. It goes up by, each one was 6x. We got that from way over here. And you can even go back, and if you look at the cosine, see, this helps out a lot. Look at the cosine. They're using the 2n here. So nothing really changed a lot other than the x. We're putting 6x in there. So the pattern is there from our easy list. The pattern that we used was there from our easy list. I say use this pattern. The only thing that changes in the pattern is the x part. And we put the 6x right there. Do you see? That's the only thing that changed in the pattern, was the x part. And in the previous problem, was it cosine or sine? We used the square root of 2 or square root of x. I think it was square root of x. And that's where the square root of x would be also in that pattern. So it's good to have the list, this pattern, and it will help you create this. And it's supposed to be a lot easier, and it really is. I mean, if you went through the way I did it, I mean, I want to find, I'm curious to find this pattern. But you can do it very easy just by looking at what the x is. Okay, I think that's it for this section. It's really not that difficult. The only problem is you have to take the series out far enough. In the previous examples, you really have to take the series out far enough to see that pattern and reduce it enough. Like question, question 3. Was it question? No, question 2, where we had to reduce it enough here to see what the pattern really was. And it was a really simple pattern after we reduced it. All right, so let me hit stop recording.